It is a well-known fact that mathematics and music have a lot of things in common, to say the least. From time signatures expressed as fractions, to note pitches expressed as cycles per second or hertz, directly related to the way we tune our instruments, the pitch A being at 440 cycles per second or 440 hertz. I mean, Pythagoras, the guy with the triangles, did a whole bunch of work on intervals in music, meaning the distances between notes. He figured out that by cutting a string in half, you will get the same exact pitch, just an octave higher, meaning double its frequency. The subject of this video is the connection between music and the Fibonacci sequence, whether that's just pure coincidence or if there's something more to it. First of all, what is the Fibonacci sequence? Well, like any good sequence, we can start with the number 0. And the next number, naturally, is 1. And then we're going to add those two numbers. 0 plus 1, it's going to be 1. The next thing we're going to do is we're going to add the last two numbers. So 1 plus 1 equals 2. And we're going to keep following this pattern. We're simply going to add the last two numbers we got together. 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, and so on. There are accounts of these numbers as early as the year 200 BC in Indian mathematics. What makes them so interesting is how often they appear in math. So much so that there are entire publications dedicated to their study, such as the Fibonacci Quarterly. Amazingly enough, these numbers don't just exist as a purely mathematical theory. They show up in nature, and that's what sparked my interest in them. They show up in the most unrelated places. For example, in the number of petals in a flower, or the arrangement of the sunflower seeds in a sunflower, or the bracts on a pine cone, or the branches in a tree, or the shape of galaxies, or the shape of hurricanes.
You probably saw this before. Let me show you how it's made using the Fibonacci numbers. Take a square with every side being 1 unit. I'm using a centimeter in this example as it is, without a doubt, vastly superior to the inch. So our numbers are 1, 1, 2, 3, 5, 8, 13, and so on. We have our first square with every side being 1 centimeter. Next to it, I'll have another one identical to it. Our next number is 2, so I need a square with every side 2 centimeters. Now 3, this side is 2, this side is 1, 3 centimeters, 5, 3 plus 2, 5 plus 3 is 8. So we have our squares with every side being 1 centimeter, 2 centimeters, 3, 5, and 8. Now the only thing we have left to do is connect two corners of every square with an arch, trying to make a continuous spiral. And we get this.
Great, we have our Fibonacci spiral. But you said we're going to be talking about music, so where is this going? Hang in there, it's coming. I just want to lay the groundwork so you know what we're dealing with here. It turns out that if you take any pair of these Fibonacci numbers and you divide them, as the numbers go higher, you're going to get closer and closer to the number phi, which is referred to as the golden ratio. Now, the number phi is an irrational number, just like its sibling pi, and we can approximate that number to the value of 1.618, just like we approximate pi as 3.14, etc. The golden ratio. Let's say we have a segment, we have a line, and we split it into two different lines, two different segments. The ratio between the longer segment of that line and the entire line that we started with is going to be the same ratio as the ratio between the longer segment and the shorter segment. And that number we called phi. There is an easy formula that will spit out this number, and I'm going to put it on the screen here for all of you who are mathematically inclined. But as it is not that relevant to this video, we're just going to approximate this irrational number, phi, to the value of 1.618. Apparently the Greeks knew about this number, and they built a whole bunch of statues and temples using these proportions. The point is, after this rather long explanation of what these numbers actually are, the practical applications of these digits produce very satisfying results in the eyes of the painters, sculptors, architects, artists that use them. So it seems like it's a good recipe to use. I mean, if Michelangelo used it, and Da Vinci, as well as Dali and Botticelli and Seurat and Van Gogh, maybe there's something to it. The question is, as it pertains to music, did composers use these numbers to craft their works? Meaning, did they mean it? Well, yes, and maybe. Or are these numbers a universal recipe that produces satisfying results independent of the medium that they're being used in? Let's take a look at how these numbers can be used to craft a piece of music. Let's start with the most obvious observations. What you will come upon first if you start researching this topic will seem like mere coincidences. Such as, in a musical octave meaning the distance or interval between two notes with the same name, let's take C to the next C higher, we have a total of 13 sounds if we count both of the Cs. We have, in our Western music theory, 8 natural notes and 5 accidentals, sharp or flat notes. So C, D, E, F, G, A, B, C, and C sharp, D sharp, F sharp, G sharp, A sharp, if I'm allowed to name them all by their sharp name. So 5, 8, 13, all Fibonacci numbers. Okay, that happened. And frankly, when I was reading this, I was a bit skeptical because we as musicians never say we have 13 notes in a key. There are 12, as the roots of those keys, the notes that give the name of that particular key, in this example C, will not be counted twice. The next example I found was the basis for all tonal harmony, the almighty triad. A triad is a harmonic construction made out of thirds, which is the musical term for start with a note and skip one, play one, skip one, play one. Cool. First note, note 1, and skip note 2, play note 3, skip note 4, play note 5, 1, 3, 5, Fibonacci numbers, okay. Except my idea of tonal harmony and the triad comes from a slightly different perspective, that of the overtone series. The overtone series explained in a very simple way as an experiment that we can actually do. It says that every fundamental tone produces a number of resonant frequencies mathematically related to that initial tone. Let's take a frequency, for example 65.4 Hertz, which just happens to be the note C. Now, the only thing we will do is add this frequency to itself a few times and see what happens. So we started with 65.4 plus 65.4, that's 130.8. If Pythagoras was right, we will get another C as we just cut the string in half, doubling its frequency and getting the octave higher. Lo and behold, another C. Let's add 65.4 to 130.8. That would be 196.2. That would be a G. Great. Let's add another 65.4 to 196.2 to 61.6, which is quadrupling the initial frequency of 65.4. So 65.4 times 4, thus giving us another C. Let's go one step further. 261.6 plus 65.4 would be 327, a justly intonated E. So right now we have a C at 65.4 Hertz, a C, another one at double that frequency at 130.8, a G at 196.2, another C at 261.6, and an E at 327 Hertz. C, C, G, C, E. If we eliminate the pitches that repeat, the extra Cs, we are left with C, G, and E, a C major triad, or a C major chord. I think that is where we're getting our harmony from nature, really. I also came across the example of Stradivarius violin, some of the most valuable instruments ever made, and how Antonio Stradivarius made his famous instruments following the golden ratio. Well, that is not that far-fetched, as we just found out that the Greeks were using phi to build statues and temples. Why not build violins, right? In the paper called Generalized Fibonacci Numbers and Music, published in the Journal of Advanced Mathematics, Anthony Shannon, Irina Klamka, and Robert van Ghent give this example and say that his violins, meaning Stradivarius's violins, are the most valuable and precious instruments in the string-playing world because of their exquisite tonal and harmonic qualities. Maybe. Though, in 2012, a double-blind study was made on 17 professional violinists that were made to wear dark goggles and then were presented with 6 violins, out of which 2 were Strads, and they were asked to identify the Stradivariuses based on their sound. 7 of them say they couldn't, 7 got it wrong, and only 3 got it right. So perhaps Stradivarius was designing his violins just like the Greeks were designing their temples, but that probably did not lead to a superior sound. If we are to take a look at a few examples of how composers use the golden ratio in their works, there are yet again a few obvious examples, the first one being Béla Bartók's music for strings, percussion, and celesta. At the beginning of its third movement, the Fibonacci numbers are quite prominent in the xylophone part, specifically in the number of notes being played, 1, 1, 2, 3, 5, 8, 5, 3, 2, 1, 1, which is a very clear example that Bartók really meant to use this sequence in crafting this musical moment. This would probably be the most obvious example of deliberate usage of these numbers. Chopin's first prelude in C major, opus 28, is following these numbers as well, with the entire piece having 34 measures, the first phrase being 8 measures long, and the climax or highest and most intense part of the entire piece being at measure 21, all Fibonacci numbers. Many other examples would follow with composers such as Claude Debussy and Maurice Ravel, and as far as going back to the times of Mozart and Beethoven. Actually, the first time I ever heard the concept of the golden ratio, even though it wasn't explained to me specifically, was when I was working my way through Beethoven's violin concerto when I was in college, and my professor said, can we start playing from the golden ratio? And I kind of brushed it off, and I didn't think much about it, but it kind of stuck with me. I've been trying to apply this knowledge of the Fibonacci numbers and the golden ratio to more recent music. In my career as teaching music, I started noticing similarities between how classical music is organized and the way let's say a pop song works. So we have the classic structure of the verse, chorus, bridge, chorus. If you look at this structure through the lens of the golden ratio, it might seem that the part of that structure, the part of that song that is different, namely the bridge, comes at exactly that point in the segment. The game I was playing is actually pretty easy. You would take any pop song or rock song where, I've been doing this with songs between the 50s, 60s to today. And you would take the total length of the song in seconds and you would multiply that by the inverse of phi, which is 0.618. And you would get a number. And you would start playing the song at that particular moment and see what you come up with. I myself have been amazed by the results in most cases. At the end of the day, I think the Fibonacci numbers and the golden ratio definitely have their place in the creation of art. I would just have to agree with one of the most interesting composers that the world has seen, Arnold Schoenberg. He said, "I don't believe in the golden ratio. At least, I don't believe that it is the single formal principle for our sense of beauty. Rather, at most, one among many."